So are you ready to start?
Yeah.
Okay. Okay, so welcome everyone. Today we're very happy to have Yongnam Lee from IBS and KAIST, and he's going to be talking about compact moduli of elliptic surfaces with multiple fiber.
Okay, thank you. So first, I would like to thank the Professor Yun-Kai Chen to invite me to here again. Okay, so let me start. Today talk is a little bit contains like surveyor talk a little bit, I think. Okay, so anyway, let's do. So first, I'm interested in this kind of surface with PG. PG means this H0KS, this geometric genus equals 0, and also irregularity, this Q is 0. Especially, more special properties, simply connectedness. So these surfaces are studied with the interest for relationality question by Castellover. So originally, if PG equals 0, Q equals 0 implies rational, but then the first counterexample was founded by Enrique and also later Godot and Campedelli. So this does not imply rational, but then people try to find what is the criterion for rationality, and then Castellover found this rationality criterion. So then, but then later, so this does not imply rational, but then later Severi asked if PG equals 0, and then simply connectedness implies rational surface, but that's still not true because of the counterexample was first founded by Dolgachev. So anyway, then now, sorry, I'm not familiar with this pointer. So now let S be a non-rational minimal smooth projective surface with PG equals 0 and simply connected. So then by the classification of the surface, this Kodaira dimension is 1 or 2, because the Kodaira dimension is 0 case is not simply connectedness. So, but then this Kodaira dimension 1 case, there are infinite families for this Kodaira dimension 1, and then there are finite families for Kodaira dimension 2, but still we do not have a complete classification for this kind of surface of Kodaira dimension 2. Then by this famous theorem by this Friedman, a smooth projective surface S with PG equals 0 and the fundamental group is 1, then is homeomorphic to a rational surface, but not diffeomorphic to a rational surface. So that is the reason why in the differential geometry people or differential topology or symplectic people are very interested in this kind of surface, because they are topologically rational surface, but not diffeomorphic. So they called it the exotic structure. So, but then these surfaces are very hard to construct explicitly. In particularly, no explicit construction for a general one in a irreducible component in the moduli. I mean, here explicit means the something like constructing by quotient or constructing by some covering or writing equations. Oh, sorry, this up. Okay, so then still there are some interesting problem which are unsolved yet is the following. So for example, I already mentioned the explicit construction of a general one in the moduli of, for example, Dolgachev surfaces, and also Kodaira dimension 2 case, and the case then also from the famous inequality for the Kodaira dimension 2 case, there is this Noether line and the Bogomolov line, Bogomolov-Yau line. So then the K-square should be from 1 to 8. And then also one can ask that this kind of surface exists over spec Z. And then also what are the explicit construction of compact moduli spaces. And then also I can ask the Bloch conjecture. These are some problem related with the zero cycles of these surfaces. And then also I can ask what's the derived category of these surfaces and also moduli of vector bundles. for example, the something like existence of Ulhihi bundles, and then also what the some algebraic structure related with the rational surfaces. So then in this talk, I will discuss some approach of some problem here using Q-Gorenstein smoothings of semi-log terminal or semi-log canonical singular rational elliptic surfaces. And here also everything, if I do not mention, then everything is over the complex numbers. Okay, so then I called S is a rational elliptic surface if S admits a relatively minimal fibration, this surface to P1, whose general fiber is a smooth elliptic curve. But here I do not assume the existence of sections. So if S is a rational elliptic surface, then there is some m, integer m, positive integer m, called the index of the fibration, so that this map is given by minus mks. If m equal 1, then that's the same as this fibration. This elliptic fibration admits a global section. And whenever m is larger than 1, then there is exactly one multiple fiber in S with a multiplicity m. If you have no more than one fiber, then it's not rational. Godard dimension is jumping. So rational elliptic surface of index m can be realized as a 9-point blowing up of P2, something like similar as m equal 1 case, where 9 points are base points of the Halpern pencil of index m. So these are the pencils of plane cubic curves of degree 3m, having about 9 base points of the multiplicity m. So, I mean, this cubic pencil case, we are considering the just 9-point blowing up of the base point, and these base points are smooth. But if you go to index m, then it's plane curve of degree 3m, but these points are has a multiplicity m. But then you can compute the exactly they give a pencil. So then also in that case, the multiple fiber correspond to the unique cubic curves through this 9 base point. Okay. So in this rational elliptic surface with this index m case is explicitly known, the construction. And then Dolgachev surface. So this Dolgachev surface is simply connected surface with PGQ equals 0 and the Godard dimension 1. So Dolgachev surfaces are elliptic surfaces. So it means again there is a fibration, elliptic fibration, with the two multiple fibers of a multiplicity P and Q, and where these PQ are relatively prime. So this relative prime is equivalent to the simply connectedness in this case. So then let pi is S to P1 be a rational elliptic surface of index M. I mean, that's just usual cubic pencil of cubics. And let M1, MS be a natural number, just choosing the S natural numbers. And then by performing these logarithmic transforms at smooth or multiplicative type singular fibers, so then we form a new algebraic surface. I will use this notation, SM1 to SMS. So this means just considering the rational elliptic surface with the section and then choosing S fibers, which are smooth or multiplicative type, then just to do the logarithmic transformation there. But then after logarithmic transformation, all fiber over this S points changing to the multiple fiber with the multiplicity M1 to MS. Okay. So then Dolgachev compute the fundamental group of this surface and show that if this only two multiple fiber and they are relatively prime, then show this surface is simply connectedness. And then we shall use this term, this as PQ. We will use, say, the Dolgachev surface of the type PQ. So to mean an algebraic surface of the form this as PQ, where P and Q are relatively prime. So the smallest case is the P equal 2, Q equal 3 case, for example. So here construction is known by using this logarithm transform over this rational surface with the section. But this is not explicit because the problem I will explain later. So anyway, this is the table classified by originally by Néron, but also do in Kodaira table of singular elliptic fibers. So this is 1. 1, 0 is the non-singular elliptic. 1, 1 means just one node, and the 1B means the B node, and the 2 is the cuspidal type, and the 3 is the tachnodal type. 4 is the like this, and these are the other type. And here all components are reduced, but here there is a non-reduced component. So this means the multiplicity 2, and here multiplicities here. And these 3 type is so this is a non-singular fiber, and 1, 1 or 1B is called the multiplicative type, or others are called the additive type. Okay. So the point is why called multiplicative type? Multiplicative type has Picard has a torsion, but the additive type has no torsions. So for example, smooth elliptic curve, then how many 2 torsion element? There are 3 non-zero torsion. But if you go to the nodal, then you have only 1 torsion, 2 torsion. But if you go additive type, no 2 torsion. Okay, so then this logarithmic transformation, which I mentioned to construct this kind of elliptic surface with multiple fiber. The one good method is this using logarithmic transformation, but this means of just replacing any given fiber of the type 1B, I mean including smooth case, in an elliptic fibration by a multiple fiber changing to the M times 1B. To be more precise, given an elliptic fibration and the point over the base, then the fiber F0 is 1B, but new fibration is M times 1B. And then except this, changing this fiber to this F0, all other fibers are fiber-wise isomorphic, but not as a variety, not isomorphic, just fiber-wise isomorphic. So then this logarithmic transformation is purely but analytic way, not algebraic method. So by using torsion group of the Picard F0, and for instance, the logarithmic transformation of the one non-singular fiber is just product of P1 times elliptic curve, and then just changing to the one fiber, one smooth fiber, then it's non-algebraic. It does not satisfy the some inequality for algebraic surface, so it's going to non-algebraic. But if one does logarithmic transformation of multiplicative fibers of a rational elliptic surface, these are not this a product type, but the rational elliptic surface with a section, then it is still algebraic if the resulting surfaces still satisfy PGQ equals 0. So now let S to P1 be a rational elliptic surface, and the XY just choosing 2 points in the base, such that considering that their fiber are smooth or multiplicative type, then one can construct this SPQ, okay? And this construction depends on the choice of the 2 line bundle of this torsion bundle, eta X and eta Y over order exactly P and Q, respectively. And then rational elliptic surface case, no Brouwer group. So then there is a unique elliptic surface as PQ to P1 with multiple fibers at X and Y associated with this invariant at X and eta Y, which is isomorphic to S over P1 minus X, these 2 points. So then considering this space of quintuples, so S is the choosing rational elliptic surface, and the X, Y are 2 points in the below P1, and eta X, eta Y are this torsion element in the here, or the P and the Q. That gives this SPQ, okay? Yeah, that's I just explained here. So then Friedman and Morgan, so they show that for a given P and Q relatively prime, the moduli space of Dolgachev surfaces with the multiple fibers of multiplicities P and Q is irreducible. And so this means that there is an irreducible complex space T of 10 dimension and the proper smooth map this car X to T such that every SPQ is isomorphic to pi inverse T. So why 10 dimension? Because the rational elliptic surface has a 8-dimensional moduli, and then we have a 2 variation of these 2 point X and Y, and the eta X and eta Y are only finite choice. So the dimension is 10 is coming. So that's easy part. Only here need to check is the why this irreducible. So why these representations give us irreducible. So then given this Dolgachev surface, one can, so conversely, if we have a Dolgachev surface, then also one can construct a rational elliptic surface with a section with at most rational double points by just corresponding Jacobian surface. If you have any elliptic surface, then you can consider Jacobian surface. So then that gives us kind of a converse construction. So then if S has no additive singular fiber, then for any X and 2 distinct points, then one can construct SPQ, because we know we can do the logarithmic transformation on the non-singular fiber or multiplicative singular fiber. And if these 2 fibers are, that type, then we can just do the logarithmic transform. But even X equal Y, then also one can consider a non-normal surface, S0, which is the semi-canonical union of rational elliptic surface of index P and the rational elliptic surface of index Q glued with the fiber, and then easy to check that this S0 has a Q-Gorenstein smoothing, like this picture. So for example, so we have 2 rational elliptic surface. So here rational elliptic surface of index P, rational elliptic surface of index Q, and so that means that we have 2 multiple fiber, one here, one the other component, and then just the gluing here in the fiber, and then smoothing to this one gives this Dolgachev surface. So yeah. Okay, and then so yeah, so that's here. But then question is but if this fiber is an additive fiber, like as a cuspidal, so choosing a rational elliptic surface like this one with some additive type fiber, so then how can we find this elliptic surface with multiple fiber varying over the point in the below? Because when we varying over the point, then this we should go to this fiber, additive fiber. Then how can we changing this part here to the multiplicative fiber? Because we cannot do the logarithmic transform in there. So that is I wanted to find what kind of limit should be there in this compact moduli. But before discussing that, this kind of elliptic surface important to studying the also moduli of surface of general type. So the reason was from the following construction. So about 20 years ago, with Jong-il Park, we construct this simply connected surface of general type with the PGQ equals 0 and the KSQ equal 1 and 2 using this rational elliptic surface with a section. For example, we consider the following rational elliptic surface. So this is a quite special one. So we have this rational elliptic, but with very special singular fibers, like as a 2 nodal fiber, 1 fiber, 1 2 fibers, but the other one is quite more singular one. Okay. But then we blowing up some point here. For example, we blowing up this point, then this original one self-intersection is 0, but after blowing up, that goes to the -1, exceptional is -1, but this proper transform is go to -4. But then if you contract -4 curve, so that producing the quotient singularity 1/4, 1, 1. So like that. So here then, but we blow a more point. So then something like this picture. So then looking at their configuration of this rational curve. So then we, for example, in this picture, we can find this kind of configuration of rational curves. So then this, we have this 5 graph of, tree of the P1, but these are the resolution graph of spatial quotient singularity. So then anyway, we can contract this 5 chain of P1 to make a singular point, 5 singular point. So then we have a 5 singular point, and then show this surface has a global smoothing, especially Kugeln-Stein smoothing. Then we can show this smooth surface satisfy this one. So this is how to construct the very special surface of general type, which is unknown before, by using the rational elliptic surface, just blowing up and then making a singular surface, and then to show this surface as a Kugeln-Stein smoothing. So then this surface is especially should be in the boundary of a KSBA moduli space. But also, yeah, previously we using rational elliptic surface with a section, but also similar method using Enrique surface, also using elliptic K3 or using Hirzebruch surface. But a little bit new idea is to using something like a double cover with the C2 invariant deformation and obstructions. And then one can construct also the following surfaces, like as a simply connected surface of general type with the PGQ equals 0, KSQ equals 3, 4, and also can construct surface of general type with the torsion, non-zero torsion case. Also something like a PG equal 1, Q equals 0, also can construct the Horikawa. So, for example, Horikawa is known that the point is we can find some singular surface in the boundary of this kind of surface. And then later, with Nakayama in the Kyoto, we extend to this construction also over characteristic P. Yeah, previous done in K over C, but also it works in characteristic P. But then later, Hacking and Tevelov Urjua, they using explicit analysis of a semi-stable minimal model program of 3, 4, they give us some insight to understand the codimension 1 boundary of the KSBA moduli surfaces. So for example, in the previous example, we have a 5 singular point. But then in that example, actually, there is no obstruction to smoothing. So it means that you can smoothing to separately this point. So then just the separate remained one singular point, like as just one, then you can find this boundary, codimension 1 boundary in the KSBA. And then, yeah, they give us some rather explicit way to how to do this processing. And then also recently, several authors obtained many interesting results related with the KSBA modular surface of general type, especially Urjua did many things. And then also we can ask the following question. So can we find the general element of the Dolgachiev surface in the boundary of some KSBA moduli of surface of general type? Because why I'm asking this one? Because we have some special construction of a Dolgachiev surface, for example, S23, but we don't have a general construction for even S23, and even other cases are also not known. So how can we find the kind of general element in some explicit way? So that's why I'm asking this question. Yeah. So for example, a general element of elliptic surface with PG equal 1, Q equal 0, with one multiple fiber with multiplicity 2 is coming from the boundary of KSBA moduli of I surfaces. Yeah, in this case, actually, this surface, elliptic surface are rather well understood, but also can coming from the boundary of KSBA moduli of some special surfaces of general type. But then also, can we find the general element of elliptic surface PG equal 1, Q equals 0, but here multiplicity 2, but higher multiplicity can find the, also from the boundary of KSBA moduli of surface of general type. But then with my former student, we construct the Dolgachiev surfaces using Kugolenstein smoothing. And also we find their explicit collection of using rational elliptic surfaces with a section and an idea in the original idea of the hackings. So now let Y be a rational elliptic surface with, for example, two 1-1 singular fibers. So most simple case, just one nodal fiber, one node, and with just two singular fibers. Then, for example, if you have this 1-1 singular fiber, from this 1-1 singular fiber, you can produce the all quotient singularity 1 over R square A R minus A with the RA equal 1. So this is the way. So for example, if your fiber is like this, you blowing up this singular point, then you have a -4 curl -1. And then you contract -4, you can contract -4. So then it looks like the same 1-1 type, but there is a singular point on the surface. But then if you're blowing up again, this here or here, so then you have changing to -5, -1, -2. But then you can contract again -5, -2. But then again 1-1 type fiber, but singular point is this quotient singularity is 1 over 9, 1, 2. But then after then here you have two choices. You can blowing up here or here. Then you can find if you're blowing up here, then it's -6, right? -6, -2, -2, or the other side is going to -2, -5, -3. But then you can also contract again. Then it go to the 1 over 6, 1, 3, and if you contract then again here. So all of them are same 1-1 type, but their singular point here on the surface are different, more high degree quotient singularity. In this way, actually, you can find all these T-class singularities from this one. Okay. And then also, if you have just one this type, then it's easy to show actually this has a global Kugolenstein smoothing. And then after smoothing, then original fiber is reduced, but after this, then it go to they have multiplicity. Because for example here, when you're blowing up this point, your exceptional divisor is actually multiplicity 2. Yeah, that's why you can produce this multiple fiber after Kugolenstein smoothing to this process. So this is kind of a new method of the construction using a singular fiber instead of the logarithmic transform. So maybe one disadvantage is here we should do in the singular fiber, but one advantage is this is algebraic method, not the analytic method. But then, for example, consider this pencil of cubics. Two. So these are three line, also this three line. But the here important thing is the all are defined over the integers. So it produces a rational elliptic surface with two 1,5 singular fibers and normal rational elliptic surface. And then we can produce this singular point, which I explained before. So then, for example, R1, R2 equal 2 case, it produces any case surface over a field of characteristic P for all prime P, because this is defined over Z, and then just blowing up and then contracting this process can do over Z. So we can produce the NK surface over any characteristic P, but we have no NK surface over spec Z. So each P we have, but not over global spec Z. This is proved by Schreier. So he proved there is no NK surface over spec Z. But then we can also ask question, because this also can construct Dolgachev surface of any type Mn over field of characteristic P for all prime P by using just this special pencil of cubics and using by previous method. But then again, we can ask, is there a Dolgachev surface of type Mn over spec Z, like the NK case? So yeah, this is still unknown, the existence of Dolgachev surface of Mn over spec Z. Okay, any questions? Okay, so then now want to discuss some moduli of especially compact moduli of this kind of elliptic surface. Okay, so first I want to explain this classical construction by Miranda using the GIT for the rational elliptic surface. So rational elliptic surface with the sections are coming from the pencil of cubics. So then considering the all cubics, plane cubics in P2, okay? And also we have a pencil of cubics, so we have a line, okay? So this gives us a parameter space for cubics, and then we need to consider line, so we are considering the Grassmannian. So GR19 be the Grassmannian variety of lines in this P9, so that corresponding the pencil of cubics, so element here corresponding the pencil of cubics, okay? And then this Grassmannian is naturally embedded in P44 by Flicker embedding. And then this PGL3 naturally acts on this Grassmannian of cubic pencils. So this acting here, so we can consider this reductive group acting here, so we can consider the GIT. So then Miranda classified this GIT. So I mean, classify means which one is stable, which one is semi-stable. So he gave an explicit geometric characterization of GIT stability of pencil with the smooth members by considering the elliptic surface XP associated to such a pencil P. So this rational elliptic surface with the section corresponding to this pencil, and then he considered this pencil by using GIT. So this P is a stable pencil. He showed the XP contains a smooth member and every fiber is reduced case. And if P contains a smooth member, and then P is a semi-stable pencil, if and only if XP contains no fiber of type 2 star, 3 star, 4 star. So these are rather bad type. Yeah, there is one fiber should be smooth. Yeah. Okay. So then also he characterized the strictly semi-stable pencil when P contains a smooth member. So P is strictly semi-stable pencil if and only if XP contains a fiber of type 1n star. And let P be a smooth, strictly semi-stable pencil of a cubic pencil, then the OBD is closed, because when you consider GIT and if you have a strictly semi-stable point, then you should consider closed point, because strictly semi-stable point can go to the just one point, to the crossed point. So then he showed this crossed point if and only if XP contains two singular fibers of type 10 star. Okay. So this is the compactified moduli of the rational elliptic surface with the section by using GIT, in the Grassmannian. But then he did again by using the Weierstrass form. So then Miranda also used GIT construct of moduli space of rational Weierstrass vibration. So now let X be a rational Weierstrass vibration. So then X is stable if and only if X smooth has a smooth generic fiber and the associated elliptic surface has only reduced fibers. And X is strictly semi-stable if only if the associated elliptic surface X tilde has a fiber of type 1n star. Moreover, two strictly semi-stable elliptic surfaces correspond to the same point if the J invariant of one n star fiber are the same. So the two constructions are quite similar. One difference is the previous case, these are crossed. Oh, sorry. These are crossed one. So that means this all of other strictly semi-stable point should go to the here. So it means you have only one boundary point. But the next one is not one boundary point. Actually, boundary is P1. So in this case, because it can be changing by J invariant. Okay, so the boundary is a little bit larger. Previously just 1 point, now it's P1. So in particular, the strictly semi-stable locus in this case is J line union infinite point, so it's P1. Okay, and the J invariant of 10 star fibers and the infinite point corresponding to the 1n star. So all of 1n star fiber go to the here, and this J invariant gives A1. And then recently, Giannardini showed describe a compact moduli of a rational elliptic surface with the index 2. So Halpern pencil of the sextic surface, sextic curve case through again a complete description of GIT stability of a certain pencil of plane sextics. But if you go high index, it's too complicated because degrees go to higher, then this computation of GIT goes to the actually unrealistic if the degree is so high. But then recently, Asher and Bezzolari used the log MMP. They extended the original Lanav's work to construct the compact moduli spaces parameterizing weighted stable elliptic surfaces which have elliptic fibration with a section and the marked fiber each weighted between 0 and 1. And moreover, they show the domain of weights admits a wall and the chamber structure. And also they construct a stable pair compactification of the moduli space of anti-canonically polarized degree 1 del Peugeot surfaces. So, the meaning here is the following. So if you consider general rational elliptic surface with a section, but then general implies that you only have a general singular fiber. So that is general singular fiber is 1-1 type, just one node. So then how many 1-1 fiber can have? This rational elliptic has a 12 1-1 singular fiber. So this is a general one. So, but then if you consider this fiber is log canonical, semi-log canonical, then only you should allow this one. For example, cuspidal, if your fiber is cuspidal, it's not the semi-log canonical. So if you want to log canonical, you should only consider this general one. But then what happening if your two nodal fiber go to collapsing? That produces the cuspidal curve or one-to type. So that depends on their J invariant, how bearing of the J invariant when you move into fibers. But when you go to the cuspidal, it's not semi-low canonical, but you can say semi-low canonical, you multiply by something like 5/6. Okay, so something like considering the pair, but changing the coefficient. So then you can allow more worse singularity. So that's the way how to do. So, but then also you can do the one-on fiber can be collapsed. So then you can produce Tack node or 1-3 type singular fiber. Okay. But if you varying, so if you only want to do semi-low canonical, you only have a nodal. But then when you two are collapsing, then only way is that you should make a two component. So, I mean, if you are familiar with the moduli of M0 and bar, when you 2 points are colliding, then you should separate these two components. So one way is a separate component or allowing more worse singularity. So that's the way how to do, they do this different compactification. Okay, so then, but also why related with the degree 1 Delpezzo, because the degree 1 Delpezzo, then anti-canonical linear system has one base point. That blowing up of that one base point are exactly the rational elliptic surface with the section. So that's why it's corresponding to this polarized degree 1 Delpezzo surface and the rational elliptic surface. So then, anyway, then there is a proper Delimonford stack parameterizing anti-canonically polarized broken Delpezzo surface of degree 1, and the interior parameterized degree 1 Delpezzo surface with the most was the rational double point. And then boundary has two boundary divisors. One is two Gorenstein semi-low canonical surfaces with the ample anti-canonical divisor and exactly two irreducible component. And there is another component, two Gorenstein semi-low canonical surface, but in this case, whose general fiber is nodal curve. So there are two components in the boundary. And also they did also some other thing, but yeah, I will explain more here. So maybe I will explain later what does it mean. Yeah, it's something similar to this twisted, twisted curve. Yeah, I will explain that. But then also using the Birkas, this general method, so he defining what is the stable minimal model, because he wanted to also find the compact moduli space whose Godara dimension is between 0 to n-1. So then if you he considered this kind of pair, semi-low canonical and the dimension D and P is some C times D, but the KX plus B is semi-ample, defining a contraction, and A is an amplitude divisor, and XP plus TA is semi-low canonical. But then if you're satisfying this kind of condition, then also one can construct the compact moduli space of this pair. So then clearly, if you apply this general theory to the rational elliptic surface, so or this Dolgachev surface, then we can find that also compact moduli space. Here, A is coming from the rational elliptic surface case. We're using multi-section. Also, Dolgachev surface case, there is a PQ section. So that using that, then we can also do this one. So theoretically, anyway, we can have a compact moduli, but only this shows the existence, does not say what's the limit and what's the corresponding surface. But then also, long time ago, I mean, Kawamata studied some classification of singular fibers of this degeneration of elliptic surfaces, but with some special condition. So he considered the semi-stable minimal model of degeneration of surfaces with the general fiber Kodaira dimension 1. Actually, he also considered Kodaira dimension 0 case, but here I'm interested in Kodaira dimension 1. But assume central fiber is normal. Okay? But also assuming no rational double point, and also assuming this map itself is not smooth. So he wanted to exclude this special fiber is smooth, also not rational double point. Yeah. Actually, this can do. First, if you have a family, then you can do the minimal model, but then some kind of base change. Then actually you can make have this kind of family. But this family, each fiber is projective surface, but it might lose this map is proper projective map. Okay. Because to removing this rational double point, yeah. And he called the moderate degeneration, but anyway. Okay, and then anyway, so if we have this family, so then there exists smooth surface B, because you can extend, so general fiber is now elliptic fibration because Kodaira dimension 1. This elliptic fibration structure can be extended to the central fiber also. So that's why we have a smooth surface, because now originally P1 and this, so general fiber is the elliptic surface, so over to curve C, but then this curve can be degenerated to the central fiber. Still, we have elliptic fibration. Maybe curve can be degenerated to several components, but anyway, we have this base the degeneration of a curve, so it's a smooth surface. Okay, so we have a smooth surface and the proper surjective map morphism from this to this surface, and whose general fibers are elliptic curve and the proper smooth morphism P2 delta. So this decompose with this surface P. Okay, so that's the first part. And then looking at this central fiber X0. So X0 is singular, so we have a minimal resolution of this surface. And then it might have a -1 curve, so we can consider their relatively minimal model. Okay. So then what he did is that he classified what is the fiber here. Okay, so looking at this scheme theoretic fiber of GX0, which passes through this singular point, original singular point of central fiber, and then he looking at the singular fiber here. And this then we have the following list. So, for example, this type, multiplicative type. So this picture is actually reverse construction. So originally we have so Kodaira dimension 1 case. So it might have this kind of fiber in the central fiber. But now we do reversely. So it means we considering the resolution of this central surface and then contracting this -1 curve on the fiber. So that gives us actually from here to the here. But now I'm explaining the reverse way. So I already explained this case. So if you have a 1-1 fiber, then you're blowing up this point here and then go to here. Also to blowing more, then you have this. But also you can do the 1N fiber here. Okay. But also you can do some special other cases. So these are cuspidal type. Okay. Cuspidal type also, if you're blowing up -4, -1, then you can contract again -4 here. So then you have a singular point here. But also blowing up here, then you have this. But then you can contract this type. But also you blowing up more here, like here to -4, -5, and then blowing up again, -6 to here. and then blowing up again this configuration. Also, you can blowing up more here, and then after you can contract this -7 to -2, then you have a singular point 1/2514, and here this one, and here if you contract these two curve, chain of curve, then you have these two singular points. But also there is another way, for example, from here, this one, but these are excluded in his list because in this case there is a 1/2, 1/1. These are rational double point. So this is excluded in his construction. But anyway, so it means that in cuspidal type, you can have only 4 type. So in the previously multiplicative fiber, you have all kind of T-class singularity can happen. But the cuspidal type, these are the only one you have. So it means I can do the also Kugeleinstein smoothing to here, this singular point. But I cannot produce the all kind of multiple fiber. I can only produce the small multiplicity if I'm using this cuspidal. And then also can do the tachinodal type. So these are the all possibility of tachinodal type. If you have a tachinode, then you can produce this one, or these are also excluded in his construction because it has a rational double point. So in the tachinodal type, only you have 2 types, this or this. Also, if you have this like as a 3, then in that case, actually only produce 1. Okay. And also in his construction, this does not occur on the central fiber. M10, 1B star, 2 star, 3 star, 4 star. 2 star, 3 star, 4 star does not occur because these are related with the rational double point. So this does not occur in his classification. So here what I want to say is in the logarithmic transformation, we cannot do additive fiber. We can do only multiplicative or non-singular. Also, this Kugeleinstein smoothing using to the singular point, multiplicative type, we can do the same way, but the additive type, this additive type, I can produce only special cases. So then how can we do this? So anyway, before that, sorry. So assume rational elliptic surface with the section has at least 2 singular fiber of this type, then one can construct also by using Kugeleinstein smoothing. Okay, so this is just we can construct the new surface by Kugeleinstein smoothing when we have this just 2 these singular fibers. But then how can we handle these kind of fibers? Okay. So these are especially cuspidal type. So the following SLT, semilog terminal surface have a Kugeleinstein smoothing to rational elliptic surface of index 1. So gluing 2 surface, x1, x2, so both are rational elliptic surface, index 1. But gluing with I0 star. So I0 star picture looks like a fiber, and then there are 4 - 2 curve. Okay. But then here I'm saying twisted. Twisted means similar. So broken means means maybe several component. But here, like the twisted means not considering I0 star type, contracting this 4 - 2 curve. So then we have P1 with 4 singular point. So I'm gluing there. So the gluing curve is P1 with 4 singular point. So that's how to I gluing x1 and x2. Okay. And the second one is I'm gluing 2. So maybe let me back to here. So in the 2 type, especially I'm considering this one. So the cuspidal can go to here. So I'm considering the gluing, now I'm gluing two surfaces over P1, gluing curve is P1, but the one side is this singular point, 1/6, 1, 1, 1/2, 1, 1/3, 1. But then what is the dual of this singular point? 1/6, 1 dual singularity is 5, 1/6, 1, 5. And these are 1, 1. And these are 1/3, 1, 2. So then if you're resolving the that singularity, that is exactly the configuration of the two-star type. So that's the why I'm using this notation. So I'm gluing 2 and 2-star. Also, the reason is that they are monodromy is the inverse. So if we want to glue this surface with this surface, and the one side is 2, so 2 means just contracting this curve to the P1, and then the other side should be 2-star. So that I can glue. And here 3 then can glue 3-star, and 4 and 4-star. So then gluing these two surfaces with this boundary, then we can show that they have a Kugeln-Stein smoothing. So then this Kugeln-Stein smoothing surface is again a rational elliptic surface with a section. So then if we understand this construction, then how can we apply this to the multiple fiber case? So then if we have a multiple fiber, so then just considering one component is the rational elliptic surface index 1. So we have a 1 multiple fiber. The other side is also rational elliptic with the M2, but gluing the same way. Then can show again this as a Kugeln-Stein smoothing. So the reason is that if you have these two surfaces, so rational elliptic with the M1, M2, then considering their Jacobian surface. Then Jacobian surface is rational elliptic surface with a section. So then now from X2, we can consider the Y, which is the gluing of two rational elliptic surfaces with the sections with the same, now gluing this curve are same, for example, 2 and 2-star type. So then we know there is a Kugeln-Stein smoothing to Y. But then you also can glue, Kugeln-Stein smoothing over X. But then your multiple fiber is located somewhere. And then this smoothing, I don't know where they go, but it has anyway Kugeln-Stein smoothing. So that gives this family has also again Kugeln-Stein smoothing to the SM1. So then we have this, for example, if PQ, then we have a Dolgachev's surface of type P and Q. So what here I want to say is that if we have an additive type, for example, if we have an originally rational elliptic surface with a cuspidal type, and then now I wanted to find some moving of the point from the base, then this point can go to the cuspidal. Then how to changing this to the multiplicative type? What I'm saying is that now I'm changing this to the gluing two surface, and then their gluing there is the 2 and the 2-star type. And then I say that this has a Kugeln-Stein smoothing. So now I want to put this surface to the boundary of the compact moduli. So that's what I want to say here. Okay. Okay, and then maybe I will explain a little bit more some special cases. Yeah, this ongoing work with Bejlari and this Donggun Lee, our postdoc in our center. So yeah, this one we just discussed 2 weeks ago or 3 weeks ago. So still not finished. So, but just I want to illustrate some example here. So now, so what's the main goal? So XB a general rational elliptic surface of index M or SM1, M2 with a multi-section. So then to find the natural construction of a compact moduli space of this X, and then also want to find the morphism from this compact moduli space to Ashev-Bergelieri compact moduli space of a rational elliptic surface with the sections. Okay. So now consider this very special case. X be a general rational elliptic surface of index 2. So we have only one multiple fiber with a multiplicity 2. Or NEK surface. So NEK surface has two multiple fiber with both multiplicity 2. In general, NEK surface has no bisection. So here, but I assume there is a bisection. So Dolgachiev surface case, multiple fiber multiplicity are P and Q. In that case, there is a PQ section. I don't know these curves are smooth, but there is a PQ section if they are relatively prime. But the NEK case, these are 2, 2, so not relatively prime. Then I cannot say the existence of bisection, but some special one has a bisection. Because if NEK surface has a bisection, so then because NEK surface quotient from G to quotient K3, so then when you construct the double cover, then you have a K3 with the section. But these are also some special condition. Elliptic K3 with the section is special. So anyway, then. But then also I mentioned these multiple fibers are related with torsion, two torsion. So then I'm considering the define a stack which is related to the two torsions. So define a stack. So just using stack is the region is the one to smooth. Okay. So and then E is elliptic curve and X plus Y satisfy this condition. X plus Y is ample, X minus Y is non-zero two torsion element. Okay. So just considering this stack. Okay, so then we have this configuration or diagram here. So, okay, so first, so we have now I assume, for example, NEK surface or rational elliptic with multiplicity 2, then we have a bisection. So bisection, if you're looking at the bisection, then bisection meet the 2 point with the multiple fiber, right? So that's the why I'm considering the moduli space of M21. So it means maybe maybe should M12. So elliptic curve with the 2 marked point. Okay, because the general we're meeting the 2 point on the fiber. And then this M21 moduli of elliptic curve with the 2 points are recently studied by person. I will say the later. He showed this stack is the blowing up of the P234, this weighted projective plane, and then blowing up of the Z. Z is this point. Okay. So why blowing up Z? Because the M21 is the elliptic curve with the 2 marked point. So then there is a map from elliptic curve with 1 marked point. So there is a map from here to here, and that is the P46. So considering why this P46 is considering by this Weierstrass equation. Okay, so then, but from here to P234 to this one is yeah. Now I did not explain the detail of the map. Yeah. Right. Actually, I'm considering more M11 bar as a moduli of elliptic curve. All right. So then this from P234 to this M11 bar is undefined locus is this point, Z. So then, so that's the why undefined point, because there is an explicit construction of this one. So P234 looking at as a A3 and A2 and sending to, for example, this point, this coordinate to here. So then it's undefined one is there, okay? And also this GM invariant morphism by this weight. So that's the why I give us a morphism from here to here, but there is a one undefined point. So that's the why blowing up over this point, then we have a morphism from here to here. Okay, so picture looks like this. Now this is P234. Okay, because then 234. So we have here but we are now considering as a stacks. So we have considering as automorphism there in the singular point. It's a mu2, mu3, mu4 together. And here we blowing up the Z, so we produce another curve here, and then, but the previous, this torsion part, this part are exactly in the below. So these are the picture of the toric picture, and this one is one boundary. So like this picture. Okay, so this is the picture of the this one, and this is the picture of P234. And also fibers of F. So fibers of F are this one. So fibers of F are genus 1 curve without a marked point, just the zero locus of this curve. So beta 4, beta 6 are here, and then just this elliptic curve. So this is the picture over here. Okay, so then if you have a rational elliptic surface with a multiplicity 2 or any surface, so that means you have a surface to the P1. So then this P1, and then we also assume bisection. So then this P1 goes to the inside of this M21 bar. Okay, so that's the picture like this. So we have this P1 to here. So that gives us also any surface case here. So why any case does not meet the exceptional? Because where exceptional coming is when 2 points are collide. That's but the any case actually you have a 2 multiple fiber, but then there is no point which so we have a bisection. Both cases we have a bisection here, and below is P1. So we have a double cover from P1 to P1. But then P1 to P1, and this is a double cover. So we have a 2 branch point, okay, because 2 to 1 map. So, but then any case, you have a 2 multiple fiber. So branch points are just coming from the multiple fiber. But the rational elliptic case, you have only 1 multiple fiber. So there is another branch point, which rise in this exceptional. So that's the picture here, and the other is here. But then recently, it's hard to pronounce. Inchiostro, he showed the chowring of this, M12. Previously I used M21, but this one, chowring. This chowring he described is exactly this one. And Y is exceptional in this case, and the X is the pullback of the O1 from the weighted projective plane. But then question is how to compute this cycle, this one-dimensional cycle inside of this chowring. Now here I'm just looking at the Enyike case. Still, we do not understand well about this case. So now just the Enyike case. So Enyike case, we have this P1 here, but that does not meet Y. So it's Y part is 0. And then looking at what is the intersecting with the X part. But also this torsion part from the below. So that using that one, we know explicitly which one is related with the M12. So then we can compute this A equals 16. So our P1's one-dimensional cycles inside of chowring is something like 16x. But then this does not meet the exceptional. So then we are considering the degree 16 monomials in P234. But then we can find that there are 10 monomers of degree 16 in P234. But we have this action, GM action. So we have 9-dimensional moduli, which are exactly coincide with the dimension of moduli surface, Enyike surface with a bisection, because Enyike surface has a 10-dimensional moduli, because it can be constructed from two logarithmic transform of the rational elliptic surface with the section. So A plus 2 is 10, but we have this bisection condition gives 1-dimensional less. So we have a 9-dimensional, and that exactly coincide with the. So moving over this curve inside of M12 gives us a 9-dimensional. So that's the explanation of this case. And also, then we can explain a little bit more how about this P1 to the M11. Okay. But anyway, maybe I will stop here. Yeah.
Yeah, thank you very much. So is there any questions for the speaker?
So at the beginning, when you talk about the KSBA compactification for surfaces of general type, you said like the construction on the rational elliptic surfaces give you some boundary points. But do you know what are all boundary points of the KSBA compactification? So are they just examples in the boundary or like the boundary?
Yeah, nowadays I think we just have some examples, and sometimes some special case people can understand just the codimension one boundary case, some special cases, but the full classification, like as a curve case, it looks almost impossible now. Yeah.
Okay, thank you.
More questions? So maybe in introduction, you mentioned at some point people study derived categories of these surfaces. Do you know what?
Yes. So, for example, what is the exceptional collections of this kind of surfaces, and maybe that's the first step to understand the derived category things. So, for example, in the Dolgachev surface case, we find the full exceptional collections by using this Kugolenstein method, and then using the singular point, and then But for example, what can you say about the other type of surfaces has a full exceptional collection, and understanding what they call the phantom.
Yeah, I was
You
going to
know,
ask.
yeah,
There's examples where phantoms
yeah,
appear?
yeah.
Or?
I think our case, but we did not find the phantom in this construction. We only find the full exceptional collection. But then I think now some papers say that they found the even phantom in the Dolgachev surface 2-3 type. Not this way, but using some explicit construction of Dolgachev. So one explicit construction of Dolgachev surface 2-3 type is considering the rational elliptic surface with index 2. So then we have a one multiple fiber, but then wanted to produce the multiplicity 3 fiber. Then this considering very special configuration, and then constructing some triple cover, and then can construct the very special Dolgachev surface, which did by I think Dolgachev. And then using that construction, they found again full exceptional collection, even phantom. But I did not read carefully the paper. So.
Okay, thank you. Any more questions?
So how much do we know about the additive threefolds? Can you apply this kind of technique to
Yeah, threefold is not far from my area, and I think many things are so different. For example, even this Kodaira's classification, this works for only over curve. So if you do the basis surface, I think the classification is different. So it's much more. Yeah.
Is
yeah.
the logarithmic transform also works for three-folds? Logarithmic transform works when you need to have exceptional divisor and fiber of the same dimension.
I think logarithmic transform, I think usually over small disk. So over surface, I think you cannot do. Yeah, only usually can do the over smooth curve, below is smooth curve, a small jump. So if the base is like as a surface, I don't think so. Yeah.
So the problem is the dimension of the base and not the total dimension of the total family. I
Oh,
thought
logarithmic transformation only can do the elliptic curve because elliptic curve has a special automorphism, right? The n times of this using torsions. So other case it does not work.
I see.
So and then also if the base should be the curve.
Okay. So any more questions? No? Okay, then let's thank the speaker again. Thank you very much.